So far during this work on integration, we've looked at the process of finding simple antiderivatives. And in this session, we're going to extend that understanding a little bit further and look at some special cases and some more advanced problems. So one of the rules that we've looked at so far is the power rule for finding the antiderivative. What I want you to think about is what might be an instance of when the power rule doesn't work? Can you find an example of a time when the power rule will not work? So this is the power rule here. If we've got x to the n, we want to integrate it with respect to x. We recognise that it's going to have to be x to the n plus 1, because when we find the derivative of this, it's going to be x to the n. But also, this would be n plus 1 times x to the n. We don't want n plus 1 times x to the n. We just want x to the n if we're finding the derivative. So therefore, we need to divide through by n plus 1. The question then is, what happens if we have a value of negative 1? So if we have x to the power negative 1, if we follow this rule, we would say x to the negative 1. So this would be x to the 0. So that's not necessarily problematic, because that would just be 1. But here we've got 1 over n plus 1. Now if n is negative 1, this is going to be 0, which means that this whole solution is going to be undefined, which is problematic. So think back to the work that we did on differential calculus, and hopefully you can see the connections. We looked at finding the derivative, so using differential calculus to find the derivative of ln x. And when we did that, we found that the derivative of ln x equals 1 over x, or indeed x to the power negative 1 for values of x greater than 0. So given, therefore, that we've said earlier integration is the opposite process of differential calculus, it should come as no surprise, therefore, that the integral of 1 over x, or x to the power negative 1, is actually ln x plus c. Similarly, when we looked at the derivative of e to the x, we found that was e to the x. So again here, the integral of e to the x with respect to x is also ex plus c in both of these instances. So, a couple of questions for you to have a go at by yourself, and then we'll go through those together. So the first question, we can rewrite that as 4 times the integral of 1 over x dx using constant multiple rule. And we've just seen the integral of this is ln x, so 4 ln x plus c. Similarly here, half e to the power t, which is just going to be half e to the power t plus c. And let's have a look at something a bit more challenging then, more generally. So here are a few questions. Think about how you might integrate those, and then we'll have a look at those together. So the first one, you've got here a quadratic which itself is raised to the power 2. So we can just expand the brackets, which gives us here 3 different component parts which we can integrate individually according to the addition rule, and if we do that, we end up with this. Similarly here, because it's a common denominator, we can rewrite this individually and simplify it, and then integrate this, each component individually, and if we do that, we'll end up with this, 3 over 2x squared plus 2x plus ln x plus c. Finally, this one, ln e to the power 2t minus 1. Ln is the same as log to the base e. So if we have log to the base e to the power 2t minus 1, then the log to the base e and e to the power will effectively cancel out, and you'll be left with 2t minus 1, and you can find the integral of that. So let's have a look then at some questions which really are probably going to be a new concept for us, but we can use our existing understanding of differential calculus to reverse engineer these rules. So suppose we have a function like this, ax plus b to the power n. If we want to find a general rule for the integral of this, how can we do it? Now the examples we looked at previously were where this is 2, for instance, and we could expand that. But what about if n was 6 or 7? We're not actually going to want to expand it first before we solve it. So can we find a general rule for the integral of this linear function here raised to some power n? So if you think about it, if we have ax plus b, we know, again, that the power here we're going to raise. So this is going to be ax plus b to the power n plus 1. And again, if we were to derive or find the derivative of that, then we would have n plus 1 ax plus b to the power n. And we don't want n plus 1 times ax plus b. We only want ax plus b. So we'd have to divide that by n plus 1. However, if you think back to the chain rule, if you were to derive this, you would also multiply that. So we've said if we raise this to the power of n plus 1, so if we added 1, the derivative would be n plus 1 times ax plus b to the power n multiplied by the derivative of the function inside using the chain rule, which would be a. Therefore, not only have we got to divide by n plus 1, so a reminder that if we bring the power down, that would be n plus 1 times ax plus b to the power n. If we find the derivative, we don't want that, which is why we're dividing by n plus 1. But we also need to divide by 1 over a to counteract the application of the chain rule. And this, therefore, is the general formula which we can use when we have a linear function here raised to some power. So let's have a look at an example. 3x plus 1 to the power 4. Again, we don't actually want to go through and expand this. That's going to take too long. So how can we use this rule to find the indefinite integral here? So just using the values here, 1 over a, 1 over 3 times 1 over n plus 1 times our function 3x plus 1 to the power n plus 1. And then we can just expand that to give us 1 over 15, 3x plus 1 to the power 5 plus c. The great thing about integration then, similarly as you can with factorizing and expanding brackets, we can actually check our answers ourselves, especially during the exam. So if we take our answer here and we find the derivative, exactly as we said earlier, if we find the derivative of this, it's going to be 5 times 3x plus 1 to the power 4 multiplied by the derivative of the function here, and therefore that's going to give us 1 over 15 times 15, which is 3x plus 1 to the power 4, which takes us back to what we had in the first instance. Second question then here, again looking at e to the ax plus b. So in this instance, we know the integral of e to the x is e to the x. So here it's going to be e to the x plus b, but again, if we use a chain rule to differentiate this, it would be e to the power x times, or multiplied by the derivative of this, which would be a. So if we found the derivative here, it would be a times e to the x plus b. We don't want that, we want just e to the ax plus b, so we need to divide through by a. So again, I have a quick example here. Find the integral of e to the 2x plus 5. So here we know that e to the x, or e to the 2x plus 5 is just going to be e to the 2x plus 5 multiplied by the derivative of this, which would be 2. We don't want 2e to the 2x plus 5, we only want e to the 2x plus 5, which is why we're dividing through by 2. Check our answer again by finding the derivative. So the derivative of this using the chain rule is going to be e to the 2x plus 5 multiplied by the derivative of this, which is 2. So if we multiply through by a half, we end up with e to the 2x plus 5, which is what we started with. Okay, so the next one here, we've got 1 over ax plus b, and hopefully you can make some links with what we did at the start of this presentation. If we had 1 over x, the integral of 1 over x would be ln x. So that's where this comes from, ln ax plus b. But again, using the chain rule, we would be multiplying, if we found the derivative here, we would be multiplying through by a. So we'd have a ln ax plus b. We don't want that, we just want here 1 over ax plus b, so we need to divide through by a. So for instance here, if we are trying to find the integral of 3 over 4x minus 2 with respect to x, we can take out the constant to give us 1 over 4x minus 2. And we know that that's going to be ln 4x minus 2, and if we were to find the derivative, this would be 1 over 4x minus 2 multiplied by 4. So we don't want it multiplied by 4, so we divide 3 by 4 here, and we can expand that to give us 3/4 ln 4x minus 2 plus c. Again, if we check by differentiating, we've got ln 4x minus 2, so that's going to be 1 over 4x minus 2 times 4. Multiply that by 3/4 as a constant, and it takes us back to 3 over 4x minus 2, which is what we wanted to get back to. Here's another question for you to have a go at, and then we'll just finish with an exam question. So for this one, we can use our first rule. If we substitute in the values, we end up with negative 1 over 18 times 6x plus 3 to the power 3 plus c, and we can check by finding the derivative. Now, if I'm trying to think this through intuitively, I'm trying to find the integral of 1 over a function. So I know that that's going to incorporate ln times the function, so that's going to incorporate ln 2x plus 3. And then if I was to differentiate this, I would get 1 over 2x plus 3 multiplied by the derivative of the central section, which would be 2. So I would actually have 2 lots of 1 over 2x plus 3, which is twice as many as I want, so therefore I need to divide through by 2. So therefore the integral is going to be half ln 2x plus 3 plus c. Now I could have just done that straight away using the general formula, which you will have in your exam booklet. So if we have 1 over ax plus b, and we're integrating that with respect to x, we could just substitute it straight into the general formula, which is going to be 1 over a ln ax plus b plus c, where x is greater than negative b over a. So I could substitute that straight in. So obviously here a is going to be 2, so 1 over 2 ln 2x plus b, which is 3, and that will give me the same answer. For question 2, I've been given, or I'm told that the function fx is the integral of 12 over 2x minus 5 with respect to dx, and I'm also told that the graph of f passes through 4, 0. So therefore I'm asked to find the particular solution for fx. So the first thing I can do then is, this is going to be, I can take out 12 as a constant, so 12 times the integral of 1 over 2x minus 5 with respect to dx. So therefore that's going to be 12 times 1 over 2x minus 5, so that's going to be ln 2x minus 5 multiplied by 1 over a. So therefore 1 over a, and a is 2, sorry, so that's 1 over 2 ln 2x. So therefore I'm going to end up with an expression 6 ln 2x minus 5 plus c. So that's the general solution, but I've also been given some information about when the graph passes through the point 4, 0. So therefore I know that 6 times ln, so when x is 4, this is going to be 3 plus c is equal to 0. So therefore c is going to be equal to negative 6 ln 3. Consequently, fx, I can then say, is going to be 6 ln 2x minus 5 minus 6 ln 3.